This conference will now be recorded.
Hello everyone. Last day we ended at this slide. So today there will be problems regarding molecular orbital theory. Okay. So the first problem regarding molecular orbital theory. The question is asking, compare the relative stability of the following species. So here how many species we have? We have O2, we have O2 plus, O2 minus and O2 2 minus. So relative stability, as well as we have to indicate their magnetic properties. Now magnetic properties, indicate magnetic properties, it means that we have to predict whether it will be paramagnetic or diamagnetic. So diamagnetic means there is no unpaired electron. If it is paramagnetic, that means there is unpaired electron present. So these four species, out of which the first one is simple diatomic oxygen molecule. The second species is, if you remove one electron from diatomic oxygen, you will get O2 plus. If you add one electron extra to O2 molecule, it will be O2 minus anion, which is known as superoxide. And if we are adding 2 electron to this diatomic O2 molecule, which is neutral, we will get another anion, which is known as peroxide O2 2 minus. So first we will consider the MOT of, that is molecular orbital MO of oxygen, molecular orbital of oxygen molecule, which is neutral one. So once you know the MO of the actual molecule, which is oxygen molecule, then you will be able to understand that if you add electron or if you remove electron, what will be the effect on the MO diagram. So this is the MO for oxygen, and sometimes it is also drawn in another way, that is, I will also show you that. But I think if you draw this type of structure in this way, in energy profile diagram, that will be helpful. That will be easier for you to identify whether unpaired electrons present or not. So when it is oxygen, the full electronic configuration you don't need, just outermost electronic configuration, which is 2s2 2p4. That means total 6 valence electrons are present. So in the left hand side we have one oxygen, in the right hand side we have another oxygen. So this is 2s2, 2 electron you can see, and this is 2p4. Similarly here also it is 2p4, 2s2. Now as it is fully filled, that is 2s2, even if you do not consider this part of the molecular orbital, then also there is no effect on the result that you are getting. Why I am saying so? Because as this is fully filled, so these 2 electron, total 4 electron, obviously the anti-bonding sigma star and the bonding sigma both will be filled. So this will nullify this one when you will calculate bond order. So obviously it will have, as if you consider it, then also fine. If you do not consider it, then also fine, because it is fully filled. But suppose if the configuration is such, it is 2s1, then it is not fully filled, it is not 2s2, then obviously you have to consider. So for saving time, when you will actually answer the question, better if you do not draw this, simply drawing only the 2p4 part is enough. So it is 2p4, 2p4, that means total 4 plus 4, 8 electrons you have to place. Now according to energy, first we have sigma 2p, then pi 2px 2py, because on out of px, py, pz, only pz is involved in sigma bonding. That means rest of the two, px, py, that will be involved in pi bond. And this is the corresponding anti-bonding of pi, and then we have sigma star. So these 8 electrons, how they are placed? See, sigma 2pz, 2 electron, then we have 4 electron here, that is the maximum accommodation possible. Next we have 6 electrons are done. Out of 8, 2, 4, 6 done. You are left with 4 electrons. Sorry, 2 electrons, right? 8 minus 6, you are left with 2 electrons. So these 2 electrons, it will be placed as, you can also draw it like this, 1, 1. Do not fill it in this way. That is both the electron, if you are filling like this and this is vacant, that is not the correct way to do it. Okay, so don't do that. Because according to Hund's rule, first you have to fill as these two are degenerate, first you have to fill one electron. After that, if extra electron present, then you can do pairing. But here there will be no pairing. So in this case, we have unpaired electron. Okay. So magnetic property, obviously it will be paramagnetic. But as we have to compare relative stability also, so once you are done with all the four species, then only you can compare stability. But as you have already seen O2 molecule, one thing you can predict that it is paramagnetic. Okay. So this is MO diagram you can draw, or another way also you can consider if you do in this way. KK means the part which is fully filled, that is 1s2. Remember we use KLMN. So this is the K shell. So this is fully filled. So that is why out of this 16 electron, we are not considering this part. And even if you do not consider this sigma 2s2, sigma star 2s2, I mean to say this part, then also it is fine. Then sigma 2pz2, just compare with this diagram. Then pi 2px2, and these two, there is a equal to sign because these two are degenerate. And then we have pi star 2px, pi star 2py. So if you write it in this way, then also you can see there are two unpaired electrons. And how to calculate bond order? Because from the bond order, you will be able to predict the relative stability. So here, how the bond order is calculated, you can see it is mentioned here, half of 8 minus 4. Now, how you are getting 8 electrons in bonding? It is basically 2, 2. So you can see 4 into 2, 8. And anti-bonding, there is 4 electrons. But again, I am saying, even if you do not focus on this part, then also it is fine. See how you will calculate bond order from this diagram. So our purpose here is to save time as much as possible, so that you can answer as quickly as possible, right? So pi, I am not focusing on this part. So here you can see total 6 electron in the bonding. So 6 minus and 2 electron in anti-bonding. So if you do in this way, then also you will reach the same answer, 4 by 2, and it is giving you bond order 2. So whether you consider this part or this part, it doesn't matter, because as I have said, this part will always nullify the bonding part. Both are fully filled. Okay. So bond order for diatomic molecule, obviously it is O2, because you know there are 2 bonds present between 2 oxygen atoms in dioxygen molecule. So this is the first species we are done. Now what about the next species? For next species, you can write in this way, or as it is O2 plus, that means 1 electron will not be present here, right? So as we have calculated half 6 minus 2 for O2 molecule, in this case it will be half 6 minus 1, because 1 electron is already removed from anti-bonding. So in this case it will be 5 by 2, that is 2.5. And if you follow this method, then also you are getting same result, 2.5. It doesn't matter which one. Just follow that one with which you are comfortable with, and that method which you can do in a faster way. Okay. So O2 plus bond order 2.5, greater than previous species. Now for O2 minus, what will happen when it is O2 minus? 1 electron will be extra in anti-bonding. So in this case, if you want to calculate bond order, now it should be half 6 minus 3, because total 3 electrons in anti-bonding, and you will get 1.5, and I am talking about O2 minus. So in this way also, 1 electron extra, as you can see, and total bonding electron, there is no change, only this number is changing. So here it is 8 minus 5, because these two are also considered, but I have not considered in the right hand side calculation, so that is why it is half of 6 minus 3. But whatever you are doing, you will always reach the same conclusion. So in this case, it is 1.5. And the next species is O2 double negative. So double negative means another electron. So in this case, the bond order should be half 6 minus 4, that means 2 by 2. Simply 1 is bond order, right? So here it is again 8, because bonding electron is not changed, and this number is increased from 5, now it is 6, and in the right hand side calculation it is from 3, now it is 4, but what we are getting the same result. Okay, just compare this. So for O2, and we'll go to previous slide, it is para because of unpaired electron. Okay, when it is O2 plus, then also there is single unpaired electron. It is unpaired electron, that is paramagnetic for 2 unpaired electron. This is also para, but this is for only 1 unpaired electron. And here bond order is 2, this is 2.5. In this case, these two species, here we have unpaired electron, right? And here also we have O2 2 minus, we do not have any unpaired electron. So this is the only species which is diamagnetic. This is also paramagnetic, right? And if we check bond order, for O2 it is 2, for O2 plus it is 2.5, and then for O2 minus it is 1.5, and for O2 2 minus it is 1. So maximum bond order we have obtained in case of O2 plus. After that it is the neutral species, that is the original species. After that it is O2 minus, and finally we have O2 2 minus. So here we can conclude this. Only O2 2 minus is diamagnetic. Remember, this question that we are discussing here, it is true that it is not MCQ type, but if you can understand this problem well, then you will be able to understand, you will be able to solve different types of questions, because based on the species O2, questions are very frequent. Okay, so out of these 4 species, only O2 2 minus, that is peroxide, is diamagnetic. Rest of the species are paramagnetic. And what about relative stability? Because in the question it is asking predict the relative stability. Now bond dissociation energy, we know it is directly proportional to bond order. Higher is the bond order, bond dissociation energy is also high. Now higher is the bond order, that means as bond dissociation energy is very high, so the molecule will be very stable. So the order of stability will be first O2 plus, then O2, and O2 minus, O2 2 minus. Okay, so this is the order of stability, max, mean. Next problem. So see, as I have said, you can get many types of question, and you can see this is also related to oxygen species. If the magnetic moment of dioxygen species is 1.73 Bohr magnet, from this information you have to choose the correct option. Dioxygen species, it means what? It means 4 different types of dioxygen. Any species can be dioxygen species. So just now remember the problem that we have solved. So the 4 species, it may be O2, it may be O2 plus, it may be O2 minus, or it may be O2 2 minus. So all these are dioxygen species, and magnetic moment is given. From this magnetic moment you have to predict out of these 4 species, in option which 2 you will choose, because in all the options there is 2, only in 4 options there are 3 species. Now when 1.73, this magnetic moment, this is basically spin only. So from spin only formula we can calculate the number of unpaired electrons. So here you can see the same MO diagram, which is for oxygen molecule, that is the neutral species. Now from the rule, that is root over n into n plus 2, which is we calculate for spin only magnetic moment calculation. So spin only magnetic moment is denoted by mu, root over n into n plus 2. Now this value is given 1.73. When it is 1.73, then both sides you can do square and you can get the value of n, which is 1. Basically when it is 1, it is 1 plus 2. That means it is root 3. Another simple way also you can remember this. We know that root 4 is 2. So root 3, it must be lesser than 2, right? So even without doing this calculation, you can understand what should be the value of n. because n can only be integer, whole number. It cannot be fraction. So either it is 1, 2, 3, 4 like this. So when it is 1.73 left hand side, obviously the value of n cannot be 2. And the next probable value is obviously 1. So you don't have to do any calculation. Now, the important point is we have this answer, that means number of unpaired electrons should be only 1. So this cannot be O2 species, because here you can see number of unpaired electron total 2, 1, 2. So it can be true for O2 plus, because when it is O2 plus, basically you are removing this 1 electron. Now it is also true for O2 minus, because now you are adding 1 more electron, but still there is 1 unpaired electron. But it cannot be true for O2 2 minus. Why? Because now there is no unpaired electron. So only these two species, for only these two species we can say that 1.73, this value of magnetic moment is possible. And you can get this in the first option, isn't it? So this is the correct option. Basically, see, if you know the molecule O2, that is the actual molecule, from this diagram we know it is paramagnetic, but it is paramagnetic for 2 electrons. But that is the information given in the question. From this it is clear it is only 1 unpaired electron. Now, except option 1, in all the other options there is presence of O2. So O2 is present in those options cannot be correct. So just by eliminating these options also, you can reach the correct option, which is option 1. Suppose if you are in hurry, you just know that O2 is paramagnetic for 2 electrons, and O2 is present in option 2, 3, 4. So these 3 cannot be correct. This is single correct choice. Obviously, the option that is left, that will be correct. Okay. Again, the same type of question that we have done for oxygen. It is not MCQ type of question, but it is good for understanding. Compare the relative stability of these following species. All these species are related to the diatomic molecule nitrogen. Similar type of question that we have seen in case of oxygen. In case of oxygen, the first molecule, which is the original species, that is O2. Then you remove electron, you get O2 plus. Here you are getting N2 plus, then N2 minus, N2 2 minus. So first thing that we will do, the MO of nitrogen molecule. Now for nitrogen molecule configuration, outermost 2s2 2p3, because it is from group 15, consider the last digit which will give you the valence electron. 2s2 2p3, this part even if you do not consider, it doesn't matter. So 2p3 2p3, and in this case remember there is difference with O2. In case of O2, first there is sigma, then pi star, then sigma. But in this case, first pi, then sigma, then pi star, then sigma star. So remember this little difference. And 2p3, that means total 6 electrons you have to place. So here we have this degenerate 2px, 2py. If you write it in this way, then also it is fine. And in 2pz, 2 electrons. So there is no unpaired electron. Okay. Now when it is N2 plus. Now N2 plus means if you consider that is it is 14, and remember in case of oxygen how we have done it, we have done it by drawing like this. And I mean to say, first you will write this and then you can understand. So same thing you can also do for nitrogen species, but I have here taken the diagram only. So when it is N2, total number of electrons 14, 7 plus 7. When it is N2 plus, it will be 13. But even if you don't focus on that, I think these are simpler. If you focus on this diagram, here when it is N2 plus, that means 1 electron will be removed. So when it is 1 electron removed, now what will be the bond order? So let's calculate bond order for N2. So when it is N2, it is half of 6 minus 0, because in antibonding there is no electron. So you are getting 3. When it is N2 plus, now from 6 1 electron removed, that is from bonding 1 electron removed. So now it is 5 minus 0 by 2, you are getting 2.5. When it is N2 negative, single negative, as if now there is one electron you are adding here. So in this case, it will be 6 minus 1. Now this is also 2.5 for different reason, but same as the previous species. And when it is 2 negative, now it should be 6 minus 2. Okay. So for n to 2 minus, it is mentioned. So if you remove this part, it doesn't matter because all these bonding and anti-bonding, it will compensate each other. So just focus on this. So whatever for n to 2 minus, we have seen it is 2. So now if we that is write in brief, what are our results? Bond order, we know it is directly related to stability, and for N2 bond order is 3, so it is maximum stable. For N2 plus it is 2.5. For N2 minus, this is also 2.5, so these two are equal, and here it is 2. So as you can see, bond order is decreasing, so stability is also decreasing. So these are the relative stability. And what about magnetic property? In case of nitrogen, that is the original molecule, there is no unpaired electron, right? So this is diamagnetic. I am writing D. When it is N2 plus, you have one unpaired electron, right? Because you are removing electron from sigma to pz. Then when it is N2 minus, then also it is unpaired electron. And when it is N2 2 minus, then also it is unpaired. So only the first species diamagnetic, rest of them paramagnetic. According to molecular orbital theory, which of the following statements are correct? So it may be one or it may be more than one. Okay. The first statement is related to O2 2 plus. O2 diagram we have already seen, and we also know, we also have idea about O2. Sorry, O2 2 plus we haven't done. We have done O2 plus. But if you have understood O2 plus properly, O2 2 plus, it is not something new. That also you can do. So O2 plus is expected to have a longer bond length than O2. Now bond length we know that is inversely related to bond order. Now longer bond length compared to O2 means what? It should have lesser bond order compared to O2. And in case of O2, what is the bond order? Bond order is 2. That means for O2 2 plus, bond order must be lesser than, it is saying longer bond length. That means bond order should be less. Then only this statement we can say it is true. So this is a diagram for oxygen. See, it is 2p4. So this is the diagram for O2. That is the neutral species. So when you are removing these 2 electrons, what will be the bond order? Only 6 electrons are present. So 6 minus 0, because in antibonding you do not have anything. So if you divide, you are getting bond order 3. So bond order is greater compared to the original species. And when bond order is greater, because of this relationship, bond length will also be shorter. So this statement is not correct. Got it? Next one statement is C2 2 minus is expected to be diamagnetic. So what about the what about the diatomic C2 molecule? Once you know that, you can easily add 2 electrons and then you can understand whether it is correct or not. So this is C2. So this part is 2s2. This is 2p2. That is the configuration. But you don't need to focus on this. So 2p2, 2p2, that means total 4 electrons. And in this case also pi comes first, then sigma, then pi star, then sigma star. Just like N2, same. But not like O2. See, in the left hand side you can see O2, just compare. In case of O2, it is sigma, pi star, sigma star. For C2, N2, B2, all these, it is pi sigma, pi sigma. So here we have these 4 electrons we have already placed. Now when it is C2, that means the next 2 electron that will enter here. Let me use different color. So these 2 electrons will enter here. Now, is it diamagnetic? Yes. it is diamagnetic because we do not have any unpaired electron. So this is true. What about C? N2 plus N2 minus have same bond order. Remember, we have done this problem. So this is for the diatomic molecule N2, where 3 electrons are present. That means total 6 electron. So we have placed it in this way. So for 6 electron, that is for original molecule N2, bond order is 3. But when you are removing 1 electron, it will be 5 minus 0 by 2. So it is 2.5. And when you are adding 1 more electron, then also it is 6 minus 1 by 2. That means both are having same bond order. This is also correct. And what about the last statement? Helium 2 plus has the same energy as 2 isolated helium atoms. Now 2 isolated helium atoms. Okay. And in this case, we have this helium 2 molecule without any charge. So we know helium 2 molecule doesn't exist because here bond order is 2 minus 2 by 0. But if you consider helium 2 plus, that means this electron will not be present. And in this case, the bond order will be 2 minus 1 by 2. That means half. That means unlike diatomic helium 2, which actually does not exist, but helium 2 plus, it can exist. But we cannot say that the helium 2 plus will be having same energy as 2 isolated helium atoms. So it is not possible. So you can compare 2 isolated helium atoms with He2, because as He2 does not exist, that means it will always remain as isolated helium. So how it can have same energy compared to the species He2 plus? So this is not correct. So here correct options B and C. Okay. Assuming 2s2p mixing is not operative, the paramagnetic species among these following 4 we have to choose. Single correct choice. Remember 2s2p mixing, what this theory is actually detailed discussion we haven't done because in our syllabus that is not required. But because of this type of mixing, remember I will just want to show you this slide. So in this slide, that is the last slide of last class. So in this slide, you can understand what is 2s2p mixing that I have mentioned. So because of this 2s2p mixing, starting from lithium up to N2, this is the energy profile diagram. Pi sigma, then pi star sigma star. But after N2, the next elements O2, F2, here it is different. Okay. So the question is asking, suppose there is no 2s2p mixing. Under that condition, you have to predict whether they are paramagnetic or not. So as you can see here, B2, C2, N2, following this energy profile diagram, B2 is having unpaired electrons. That is, it is para. C2, N2, no unpaired electron. These two are done. But suppose if this 2s2p mixing is not present, so in that case, what you will do? You will consider sigma first, then pi, pi star, and then sigma. So basically, you will consider now the situation like O2 and F2. So that is the essence of the question. So now we will go back to the actual question. So this is our question, right? So first, except this B2, C2, N2, let's see what about BE2, because that is we have not done it before. So BE2, we know it is having total atomic number is 4. That is, it is basically 1s2, 2s2, but you don't have to focus on this. Just consider 2s2 and 2s2, 2 electron. So basically here also bond order is 0. So it doesn't exist. So question of paramagnetic does not arise. Next, consider B2, C2, N2. So the same picture you have already seen. So when it is B2, and this picture is based on 2s2p mixing present. But suppose there is no 2s2p mixing, then this part, how it will change? It will change like this. So under this condition, for B2, it is boron is basically 2H2 2P1. That means just focus on this P part. So if you focus on that, only 2 electron you have to place, and for sigma the capacity is like this. So now see, it is diamagnetic. So when you are not considering 2H2, then this species is no longer paramagnetic like before. Now it is diamagnetic, and we have to answer which species is paramagnetic. Now if you consider C is basically 2H2 2P2. That means total 4 electron for C2. So this 4 electron you will place like this, 2 already there. Now it is becoming para, unlike the previous case. So C2 should be the correct option. What about N2? In case of N2, it is 2H2 2P3. So 2P3 means 3 plus 3, total 6 electron. So next 6 electron we have already placed here, 1 2 3 4. So 2 more electron, that should be like this. So this is still dia. So for N2, whether you consider 2H to be mixing or not, it is still dia. But for B2, it is reverse. For C2 also it is reverse. So previously B2 is para, now it is dia. Previously C2 is dia, now it is para. So that is why option 3 should be the correct option. Okay. Among the following, the molecule expected to be stabilized by anion formation. So see, directly it is not saying anything about magnetism, or it is not asking anything about bond order or stability, but it is saying something about stability by anion formation. That means suppose you have any species X, it is accepting 1 electron and it is converted to X minus. Now this process will be feasible in which case? That is present in the question. Expected to be stabilized anion formation. That means X minus is more stable compared to the original species. And how you will understand? So you just have to check the bond order for these two species. So suppose the bond order for the anionic species is greater, so obviously it will be stabilized. So what you have to do for all these species, you have to compare original species and the species after 1 electron gain. Just compare this. If there is increase in bond order, that should be your correct option. So we have total 4 species. Now O2, C2, F2 we already know because it is symmetrical diatomic molecule, but NT is hetero. There are 2 different atoms that we have not done before. So this is basically NO. This side we have nitrogen, this side we have oxygen. Now for nitrogen it is 2H2 2P4. For oxygen it is 2H2 3 2P4. So here this side we have 4 electron, this side we have 3 electron. Total 7 electron you have to place. So here also first pi, then sigma, then pi star, then sigma star. So 3 plus 4, 7 electrons. How we are placing it? Here maximum capacity 4, then 2. That means 6 electrons we are done. 1 more electron is present in pi star 2py or 2pz, whatever. Now this is for NO, but if you consider NO minus, there will be 1 electron extra, isn't it? So this 1 electron extra you will place it. Now calculate the bond order. So previously the bond order is 6 minus 1 by 2, but now it is 6 minus 2 by 2. That means it is 2. So in this case you are moving from 2.5 to 2. So obviously it is, you are not moving from towards more stability. So this should not be the correct option. And what about the other species? So bond order, if you consider all the electrons, that is here it is written 10. How it is? Because here 2s1 is, that is also considered. But even if you don't do so, it is fine. So now come to O2. So when it is O2, we know the bond order is 2. But when it is O2 minus, there is 1 electron extra, and now it will be 6 minus 3 divided by 2. I'm talking about O2 minus. So this is 1.5. So in this case also from 2 to 1.5, obviously you are not reaching stable species. Then what about C2 and F2? So for C2, remember it is 2p2 both sides. So total 4 electrons we have in this way. So for C2, when it is neutral, it is 4 by 2. 4 minus 0 by 2 bond order is 2. But when it is C2 minus, there will be 1 electron here. So this is also under bonding. So now it is 5 minus 0 by 2. So see, when it is C2 minus, you are reaching from 2 to 2.5. So this should be the correct option. And for, you can also do it in this way. And for, so this is given for C2 minus, as you can see here, pi 2px2, 2py2, and then sigma 2p1. So Z is considered as molecular axis. But here bond order is considering calculated considering all the electrons. But for simplicity, you can focus only on this part. That also will give you same result. Then for F2, it is sigma first, then pi star, then sigma, and it is 2p5 for fluorine. So total 10 electrons we have placed in this way. So if you simply consider for fluorine, it is basically total 6 and minus 4. So you are getting only 1. We know F2 molecule bond order, it will be 1 because it is like this. And F2 minus, now there is one more electron here. That means now the calculation will be 6 minus 5 by 2, which will give you 1 by 2. So you are reaching from bond order 1 to 0.5. So you will not get a stable species. So that is why C2 is the correct option. Okay. So this is the final result for NO to NO minus. We are moving from 2.5 to 2. For O2, 2. So these two not possible. This is also not correct. This is correct because from 2 to 2.5 we are getting stable species. A homonuclear diatomic molecule shows 2 electron magnetic moment. Now what this means? Shows magnetic moment for 2 electron. So if you remember this formula, which we have already used in one of the problem in today's class. So it is giving you a magnetic moment for 2 electron. That means when it is 2, it is 2, 2 plus 2. 2 into 4. So it is root 8. So something lesser than 3 because root 9 is 3. So root 8 will be something lesser than 3. Okay. So important point is you don't just have to do this calculation. Important point is this homonuclear diatomic species is having 2 unpaired electron. N is 2. That is the important information which will help you to answer the question. Next information given, the 1 electron and 2 electron reduced species. So suppose the species is X. I don't know what this species. It may be N2Cl2O2 or B2. 1 electron, 2 electron reduced species. That means when it is gaining 1 electron, it will be converted to X minus. When it is gaining 2 electron, it will be converted to X2 minus. So this 1 electron and 2 electron reduced species concern, we do not know what species, obtained from above gas molecules. Basically, you can see all these are gas molecules. They can act as both oxidizing and reducing. So these two species, it can be oxidizing agent or it can be reducing agent. That is the second information. The third information, when the gas molecule is 1 electron oxidized. So now what you are doing? Now you are doing some oxidation process. So you are removing electron, you are getting X plus. I can write it here too because all the species are diatomic. So that I can do. So this species, that is the 1 electron oxidized species, now the bond length is decreased compared to the neutral species. So in this case, bond length is decreased. That means bond order should increase compared to X2. So these are the three information. First information, total number of unpaired electron 2. The second information is this, and the third information is this. From these three information, you have to understand which answer will be correct. Now it seems as if it is very complex, but if that the question is framed in such a way so that it can fool us. But if you think calmly, this first information is enough to answer the question. So why I am saying so? O2 we have done several times, and remember there are 2 unpaired electrons in O2 molecule. So it is matching with this first information. So let's check the other 2 information, that is O2. So better checking the other 2 information, I will suggest just check that the other species whether there is 2 unpaired electrons present or not. Okay, so for N2 we know there is no unpaired electron, it is diamagnetic species. And what about B2? B2 is basically 2s2 2p1, so 2p1 both side, and we will have one, that is 2 electron. If it is sigma, 2 electron will be together. If it is pi, then 2 electron it will not be together. Okay, so this is for nitrogen, the energy profile diagram that you are seeing, and here we do not have any unpaired electron. It is nitrogen. But suppose if it is B2, there will be only 1 electron like this, and both this electron that should be present in sigma. So there is basically no unpaired electron. You can also check it here. That is for B2 what happens. So for B2 it is basically pi, then sigma, then pi, then sigma. So there is 2 unpaired electrons present, right? Sorry, this diagram there is it should be here. Okay, so for N2, whether you write pi below or up, it doesn't matter, it will always give you diamagnetic result. But for B2 there is 2 unpaired electron. Here also we have 2 unpaired electron. So we have to choose anything between these two, because if you consider chlorine, so there is one mistake, it should be below, it should be up. So this is for B2, this is for N2, this is oxygen, and this is chlorine. So for chlorine it is just like fluorine, it is instead of 2p5, now it will be 3p5. So 3p5 both side, total 10 electrons we have to place. And here the energy profile diagram, it is also just like F2, sigma first, then pi star. So these 10 electrons, how we have placed in bonding 6, and here we have 4. But important point is there is no unpaired electron. So these two you can cancel, and we have to choose between these two. So first information is helping us to eliminate 2 options. We are stuck between O2 and B2. Now the second information that, okay, rather than checking the second information whether it is oxidizing or reducing, the third information you can easily check, because you just have to add one, you just have to remove 1 electron. So when you are removing 1 electron from B2, you have now B2 plus. So originally for B2 the bond order is 1, isn't it? Because it is 2 minus 0 by 2. But when it is B2 plus, it is basically 1 minus 0, because you have already removed this electron. So it is now 0.5. That means from bond order 1, now you are reaching low bond order. That means your bond length is decreasing. But here it is mentioned that the gas molecule, when it is oxidized, the bond length is decreasing. So in general, if I write, it is X2 to X2 plus. Here bond length is decreasing. That means bond order should be increased compared to the original species. But in this case, in case of B2, it is 1 to 0.5. So it is not matching with this information. So this from this information we can choose that this should be the correct option. What about the other information? That also let's check. So when it is 1 electron reduced species and 2 electron reduced species, that means 1 electron and 2 electron reduced species means it is talking about O2 minus and O2 2 minus. Now we know that for this type of species, that is peroxide and superoxide, they are basically having the capacity for oxidation as well as reduction. So this information, it may not be so helpful because if you don't have the previous idea, that is just from MOT, you cannot understand. But the first information that it is a 2 electron paramagnetic magnetic moment value, 2 unpaired electron, and the second information that 1 electron oxidized species, that means from X2 after removal of electron you are getting X2. So the first information is helping us to eliminate chlorine and nitrogen, and the third information is helping us to eliminate B2. In this way you can reach the correct information, which is O2, even without considering this second information. Fine. Here we have to find number of diamagnetic species. Total how many species are given? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is an integer type of problem. Atomic numbers are given. So that information is there. So for H2, whether it is diamagnetic or not, it is very simple. We know H2 it is containing 1 electron, it is 1s. So when you are placing this electron, yes, it is diamagnetic species, right? Now when it is helium 2, helium 2 plus, helium 2 plus means 2 electron both side, but as it is helium 2 plus, I have written 1 electron here. So it will be like this. So this is basically not diamagnetic, this is paramagnetic. Then the next species, that is lithium 2. Lithium 2 is atomic number 3. That means it is 1:2, 2s1. So both side 2s, 2s, 2s1, 2s1. So it is just like hydrogen. So this is also diamagnetic. Now come to the next one, that is Be2. So when it is Be2, it is 2h2 both side. So here it is diamagnetic and basically bond order 0, so it does not exist. So we cannot say this is paramagnetic. Okay. Then the next species is boron. Now for boron, it is 5 and it is 2s2, 2p1. So I will just consider 2p. We don't need to consider 2s. So only 1 electron for boron, that is B2. So 1 electron means, sorry, we also have to consider pi orbit. Okay, let me write it. So for B2, C2 and N2, we will draw a common diagram. So pi first, then sigma, then pi star, and then sigma star. So when it is B2, it is basically 1 electron. So both this electron you will place like this. So this is basically paramagnetic. Now if it is the next species, that is C, now it is 2p2 both side like this. So now there will be 2 more electron, but not paramagnetic. So this is diamagnetic. When it is 7, that means, sorry, it should be like this. When it is 7, total 3 electron. That means now in sigma you will feel, so N2 is also diamagnetic, right? And what about O2 and F2? Remember, in case of O2 and F2, we will just focus P, and first sigma, then pi star. Because of this 2s2p mixing fact, it is different. So when it is oxygen, that means it is 2p4. So 2p4 means total 8 electrons. So this is paramagnetic. Actually, we know it is paramagnetic. So 2 is paramagnetic. And if it is F2, that means 1 electron now will be extra both sides. So F2, it is basically 5. And this extra electron you will place like this. So this is also diamagnetic. So out of these 9 species, paramagnetic, paramagnetic, paramagnetic. So out of 9 species, we have to subtract 6. Okay. Sorry, we have to subtract 3 because in the question it is asking the number of diamagnetic species we have to find. So 3 is number of paramagnetic species, and this is total. So when you subtract it, you will get 6. So this is actually the total number of diamagnetic species. So here answer should be 6. Total 6 diamagnetic species present. Okay. So we do not have any more problems, and we are almost at the end of the session. So we will end here. Thank you for listening.